and we'll follow the same textbook. And I hope you all have the textbook and you'll be able to read along, whenever you find time. And I just want to really caution you that this is a fantastic material. MRI is very complicated, but yet it is very powerful, and it is powerful because it is very multidisciplinary. And so I would request you to essentially use this video recording just to ensure that you get the feel for the subject, feel for the concepts. I'll try my best to show some animations, give some vivid examples, so that the concept gets into your brain. After you get the concept, you have a feel for the concept. You have to read multiple times the textbook, few other sources wherever you get a handle. You have to keep reading from multiple sources to have your own imagination of the concepts that come in MRI. So by no means me covering this in maybe over 8 to 9 lectures, that will squeeze down to maybe 4 to 5, 6 hours or something like that, is no means doing justice to the topic itself, like it has been with most other modules as well. So it's a very introductory material. Okay, so let's move on. We'll quickly do an overview. The overview will not span more than 2 3 slides, and then we'll get into the details of nuclear spin, precision, excitation, relaxation, and contrast mechanism. So as you will notice, this is not complete, right? This is just the block of the physics of MRI, right? Like we cover every other module that we have covered. We have covered the physics, we have covered the instrumentation, reconstruction, and then finally the image quality aspects. So similarly here, we'll try to cover the MRI physics over maybe 3 lectures or something, there about 2 to 3 lectures, or even slightly more, and then we'll spend a lot more time on the imaging, reconstruction, image quality. Okay, I did pick several materials from several locations. As far as possible, I've tried to list the references so that you could go check it out yourself. So to start with the modality itself, a grand overview. The first thing that hopefully strikes you is you look at that, you see NP 1952, NP 2003, NP 2003. What is NP? NP is Nobel Prize, right? So you can see as early as 1945, it was called nuclear magnetic resonance. This was about before the World War II, right? After World War II, nuclear became a word that is taboo. So instead of calling it nuclear magnetic resonance, it became magnetic resonance, and then it was adapted to imaging, right? And so it became magnetic resonance imaging. And so first you have Bloch, who got a Nobel Prize for essentially coming up with the understanding of nuclear spins and how you can, come up with scheme to characterize the spin properties. And then Lauterbach and Manifold, they put a system together and they used the magnetic resonance principle, the nuclear magnetic resonance property, and convert that as an image. Of course, I did put one more Demadian there just because there is some references that suggest that Demadian also had the version before the others, but then he didn't really get a Nobel Prize. But he had probably also contributed a lot to demonstrate the NMR for imaging. Of course, this is non-ionizing. That is a big difference from what we have covered so far. We have covered ionizing radiation-based projection radiography, X-ray, CT, and then non-ionizing radiation-based. We talked about ultrasound, right? So this is another one which is non-ionizing, and one of the single most advantages, if you actually look at it, is compared to ultrasound, which was also non-ionizing. Here we could do whole body imaging, right? That is a big advantage. Of course, apart from that, it can do fantastic soft tissue imaging and functional imaging. Remember, most of the ultrasound lectures that we covered, topics we covered, images that you would have seen, we didn't really see, we couldn't penetrate bone and go into the skull and see the brain. Most of it was abdomen, surface level. Whereas MRI, It's so powerful that you could actually do your head scans. That's and therefore functional imaging here is also very powerful. And I'm sure you would have seen several MRI applications. We'll try to understand, what is the versatility of this. So first, it provides a high resolution anatomic structure, and compared to your X-ray CT, here you could also get very good soft tissue contrast. Remember the figure 1.4 that is shown. This is the same figure we started looking at when we did X-ray CT, as well as um, in the introduction class we also talked about PET spec, the C image that you see, and of course the MRI. So now what we will attempt to do is, yeah, we knew from before MRI probably had very good contrast of distinguishing several different soft tissue within soft tissue, unlike CT, which was very, or X-ray based, which was very good with the bones, right, especially. And then it has no exposure to harmful radiations, but most importantly, it is very complex system, and therefore, access to it is very difficult. It needs dedicated setup that all pushes the access and cost. And of course, patients who go into that big gantry that you would see, it could be claustrophobic, and so patients could feel uncomfortable because the data acquisition takes more time. And this is not, I mean, this is being addressed at several levels. It is becoming, the data acquisition is coming down, but still it's one of, not anywhere comparable to your ultrasound where we did 30 frames per second or 40 frames per second frame rate. So here is an example image that is, top row you see A and B, you see the X-ray image, bottom is your MRI. And what you see and what you don't see both tell a big story. What you see in the top row is, if you see the bone, nicely you could get the shape, size, you could see the bone. If there was a crack, you could find out. So X-ray had its role. But look at the images in C and D, which is from MRI. Not only do you see the bones, you also see the tendon, you see the meniscus, you see the muscle, you see tissue, you see a whole lot more than what you saw in the X-ray image. And not only that, the quality also seems to be very good. So what you would like to do is, okay, you do see a lot more, but you really do not know at this point of time what it is, right? Looking at the image, you say, yeah, it's very good compared to the top A and B, C and D are good. You are able to see much more. But what is that much more? We really do not know, in the sense that the top, you know what is white, what is black, what is gray. Right? You know the units. It's nothing but related to the X-ray attenuation coefficient of the material at that location. That is what you are seeing. Whereas here, you really do not know what physically that white or gray or black means. So the goal that we started asking ourselves at the beginning of the courses, what do you see? You see whatever you want to see. What is that we want to see in MRI? That's what we will uncover in the next several lectures. Okay. So first and foremost, we'll start with the basic concept, nuclear spin. What is a nuclear spin? We talked about atom, nucleus, electrons, protons, all of this we did in the X-ray physics when we started. So we were restricting ourselves to the electrons, and the behavior of the electromagnetic energy or X-ray energy with your electrons was exploited in X-ray based imaging. And that time we mentioned about something about the nuclear, right? We said nuclear medicine, right? PET, where we talked about radioactivity. Essentially, the signature comes from the radioactive decay that happens at the nuclear, so that was nuclear medicine. Here also we are talking about nuclear spin. So that means it gives you a clue. Nuclear, when we talk about here, we are interested in the nucleus part of the atom. What is there in the nucleus? You know that. What is that? It is neutron and protons. Neutron don't have any charge, so protons has positive charge. So when we talked about electrons, we talked about electrons spinning around the nucleus in shells, K shell, L shell, M shell, N shell, all those things. What happens to the proton itself? Is it just standing there? No. The protons, which are positively charged, are also spinning about its axis. So to just recollect, we know nuclei consist of protons and neutrons, and so nucleus is actually positively charged, and we know, and the spinning is an intrinsic property. Like you have charge, you have mass. Spin is also a very fundamental property, and it turns out that spins can be in multiples of half. That means it can be multiples of half. It can have a positive spin or a negative spin. What does it mean? You can have clockwise spin or anti-clockwise spin, right? So when you have a charge that is spinning around, you can start to imagine that as nothing but a current loop, right? What happens? Why are we interested in imagining this to be an equivalent of a current loop? The moment you have a current loop, that is, you have a charge that is moving around in circles, then you would expect you will have a magnetic field associated with it. So this is the key. So you have nucleus. The nucleus has protons which are positively charged. The protons are now spinning. So if you view that as a charge that is doing in circular loop, that is nothing but a current loop. That means you would expect to have a magnetic field that is there present along with this charged particle that is spinning. So it produces its own magnetic field, however small it is, right? So what happens when you have a magnetic field and you subject that to an external magnetic field? Well, you may not expect anything if you really don't connect it, right? So where else have you been exposed to a magnetic field and external magnetic field? Your simple bar magnets. Take your magnets. You would have seen the 8th standard, 9th standard experiments. You take a magnet and place it on table. What will happen? It will try to align to external field. What is the external field here? Your Earth's magnetic field. So you have a magnet. You leave it in the presence of external magnetic field, which is the Earth's magnetic field. What do you see? It is actually rotating, right? It is experiencing a torque so that it now aligns itself to the Earth's magnetic field. So naturally, that means if you imagine all your nucleus is having spin, it is charged and it is spinning, therefore it has a tiny magnetic field. If you subject this tiny magnetic field to an external field, you would expect the same thing. That is, the spins should experience a torque so that it becomes in alignment with the external field. Okay. So before we proceed, just imagine. So this is what we are talking about. We have multiple of these, many of these in our tissues. You have a spin charged particle, so you have a magnetic field. Okay, a vector. So I said you could imagine that it is very similar to a bar magnet. A bar magnet has a north pole, south pole. It has magnetic flux lines, so it will align itself to the Earth's magnetic field. Likewise, you have your charged particle that is spinning, so you have a magnetic moment vector mu. So each nucleus has a magnetic moment mu, which is parallel to its spin axis, right? So you have, if you want to really imagine, you imagine, like we always say, right? I've been saying the X-ray part, I told, imagine yourself as nothing but distribution of mu. Mu there was your X-ray attenuation coefficient to X-ray energy. So you got just distribution of mu. In ultrasound, we said we are just distribution of acoustic scatterers. Here I'm saying we are nothing but distribution of this magnetic moment vectors. So we are just spinning charges all through the body. So the good news is, since we have so many of, what are we composed of? Water. So that means you have H2O. So you have two hydrogen nucleus. So you have plenty of hydrogen. So for all practical purposes, we will imagine that you have hydrogen nucleus is all spinning all over the body. You have several localized places, and each one has its own tiny magnetic field. So what does basic principle of MRI do? Basic principle that is captured is, because of this magnetic field, what happens? I'm not I'm not really charged, right? So if you bring a bar, if you pick an iron rod, I'm not attracting it. So I'm not really having a net magnetic field. So if I take the bar magnet, it may attract iron, all your placeholders. But that's not happening, right? You and me, I'm saying we are all hydrogen, we all tiny magnetic field, but you're not really attracting all the paramagnetic objects. Why is that? That is because we have all the spins, we have all the micro spins, but then it is all in each random directions, and therefore all the magnetic fields due to the individual spins cancel out. So by itself you are not charged. But what will happen? If I take this hydrogen, it processes a spin, but it is all over the place and therefore it is getting cancelled. So I don't have a net magnetization. But then if I start to put myself in a, so imagine that you have several different bar magnets. I throw them in the table. Each one starts at different orientation. But then because of Earth's magnetic field, everything will turn around and align itself to the Earth's magnetic field. They would have started at different locations, different orientation depending on how I threw it. But then it will align itself to the Earth's magnetic field. Similarly, my hydrogen atoms are all in different locations having different magnetic moments in different directions. But the moment I subject it to an external magnetic field, all the microspins now will try to align each other. Okay. So that is what is exploited. So we all have hydrogen atom, there is a spin naturally, therefore there is a microscopic magnetic moment vector. But by itself, we are not, there is no net magnetization. But when I put this patient in an external magnetic field, all the small spins start to align itself in the direction of the external magnetic field. For the purposes of discussion, we'll say z-axis is the direction of the magnetic field. So we'll say, at least in the physics part, before we go to instrumentation, the physics part, we'll say the z is actually going from floor to roof. That is your z-axis, and therefore your xy plane is the floor plane, right? So what happens is you have a rotating magnetic field. So if you have an external magnetic field that is along the z direction, then all the microscopic spins, all the moments will start to align itself in the same direction. And therefore you have a net magnetization, or what we call as bulk magnetization vector, that starts to rotate. Of course, we'll get into the details of Larmor, frequency at which it is rotating, all those things we'll get in. But you can actually imagine that there is a net magnetization that is going to be having a direction in the z, and that's also going to have some components on the floor. Okay. So now the whole idea is we have this magnetization, we apply an external magnetic field, so the spin starts to align. We apply another rotating magnetic field so that we make this net magnetization vector dance to our tunes. That's essentially what it is. So how it dances to our tunes, each one will behave differently, and therefore we can differentiate one material property based on its spin properties and how it tunes to your dance. How it dances to your tunes to the other location which does not. So the spin property, right? What are those? We'll look at it. Is what is changing from location to location, and we are trying to characterize the spin property and trying to distinguish one location from the other location. That's what we do. Because here I've stopped with the NMR, which will be the physics part of it. How is this signal, starting with the signal, how do we make an image, will be in the second part. I think this is a good time to stop to